Hello, welcome to today's lesson of section 7.4, which is titled Logarithms. As you can see from the first line, it is a brand new concept, and it's also very, very important. If you talk to anyone who's taken Algebra 2 before, and you ask them what did he remember from that class, they almost always will talk about logarithms. Some will probably talk about logarithms in angst, because it can be a tough concept, especially if it's not taught right, but my hope is that this video will help you to understand it, and then of course we'll have a discussion on it and a practice problem session on it on Friday of this week. So to understand what a logarithm truly is, it's simply going to be the inverse of an exponential function. Because if you took an exponential function and try to find its inverse, you'd switch x and y. You gotta then solve for y to truly get the inverse function, but you'll see we have a problem. So let's say I take the most basic exponential function, y equals vtx, and we'll assume a equals 1. Okay, so you have y equals vtx. If you now try to find the inverse, remember we switch x and y. We already talked about this last week. But how do we get y by itself? So that's where logarithm comes into play. Logarithms allow you to get y by itself. Or for short, we can say logs. So how does it work? Well, x equals b to the y is equivalent to saying the following. If I've thoroughly confused you, then I accomplished my task. I'm just kidding. Let me help you understand this. So I put a star next to it. It's a very, very important concept. It's kind of like the key for this whole chapter. X equals b to the y. If you had that, so you start with y equals b to the x, you switch x and y, so now you got x equals b to the y. In order to get y by itself, we write it as a logarithm, where you have log, the b now becomes a subscript, and x is now your input, and you have y all by itself. So it's just a rearrangement. If you want to think of it this way, it's a rearrangement of variables. Some other things to keep in mind is that your base is going to have to be greater than 0 and cannot equal 1. Also, your x is going to have to be greater than 0. Let's do some problems first. Like I said, if I could keep talking about logs all day, but let's do some problems. This will hopefully make a little more sense. Right now, it might seem a little confusing, but if I do some problems, this might clear it up. So let's look at example 1. So you have log base 3, 81 equals 4. Now again, remember, log base b x equals y. So in this case, our b equals 3, our x equals 81, our y equals 4. It's equivalent to x equals b to the y power. It's almost like you're shifting this to the other side and raising it to the y power. So if I rewrite it, 81, that's x, equals 3 to the 4th power. So that's how you rewrite. Okay, the structure's a little confusing. Rewrite the equation in exponential form. My apologies. These were originally logarithm form. So 81 equals 3 to the 4th power. So here, 14, 1, equals 14 to the 0 power. So you keep x where it is. Whatever you're taking the log of, keep it where it is, and simply take the base and raise it to the number on the other side. And it's true, 14 to the 0 power is 1. Part A, it's true, 3 to the 4th power is 81. So it's simply just a rearrangement of numbers here. What I really want to get at are problems like, or the parts in number 2. So I'm putting a star by this because it's also a very important problem. And if you want to follow along, you can go to example 2 on page 5 in the book. You can or if you want some extra resources to look at. So log base 4 of 64. And again, the way we say it log base 4 of 64. That's how we say it. What does that equal? So really what you're asking yourself is the following. 4 to what power equals 64? Well, if you think about it, we can rewrite it log base b x equals y. So x equals b to the y power. So in this case, our x is 64 is going to equal 4 to some power. In this case, our power is going to have to be 3, because 4 to the cubed equals 64. So it's almost like you're undoing an exponent in a way when you're using logarithms. Here, log base 5 equals 0.2. So 5 to what power equals 0.2. So 5 to the y equals 0.2. We know 0.2 is 1/5. So y has to equal -1, because if you raise 5 to -1, you would get 1/5. So instead of actually doing powers like 5 squared is 25 and 5 cubed is 125, we're actually going backwards now. We're trying to figure out the exponent. We know what the base is, we know what the power equals after it's worked out, but what is the exponent? So it's like trying to find the exponent if you think about it. Like finding exponents. So in this case, 125 equals 1/5 to the y power. Y would be -3, because you have to flip it over to make it 5 and then cube it. Pause the video, see what you get for D. Okay, if you said 1/2, you are correct. Set equal to y. So 6 equals 36 to the y power. And if you think about it, square root of 36 is 6. How do we express square root as an exponent? We know that's 1/2. Another thing I want to talk about are common logs. If you don't see a base, so no base is present, you assume it's 10. So common log is base 10. Natural log, if you have this, right, ln x, this will be, and you can see in the calculator as well, so I think it's on the left side on your graphing calculator, it's base e. And we've talked about e the last time we met, I think during block number 2 of this week. So e, remember that's a number, natural log, that's a natural base, so ln x is log base ex. Number 3 is a little tricky. So here we have an exponential function, but we have a logarithm inside an exponential function. Now remember, b to the y equals x, same thing as saying log base bx equals y. So our b is 10, our y is log 4. So if I shift things around, remember my base is 10, I don't know what x is, so I'm going to set this equal to x, because this is in the exponential form right now. Log base 10 of x equals y, which is log 4. And we already know log 4 is common log, that's already base 10, so y has to equal 4 in this case. Sorry, x has to equal 4 in this case. So it's almost like the 10 is the base for the exponential function, and the log, because that's also base 10, it's like they undo each other. So you get 4. It's kind of like square rooting x squared. We know that's going to be like x, or abs of I of x if you want to get more technical about it. Here, log base 5, 25 to the x. So log b x equals y. Remember, the same thing as saying x equals b to the y power. So our b is 5. And you can think of x, I know it's kind of confusing, but you can think of this whole thing here as being like the x. So when we shift it, keep 25 to the x where it is, and you raise 5 to the y power, because I'm setting it equal to y in this case. 25 is 5 squared. 5 2x equals 5 to y. Remember, we set this whole expression equal to y, so we set y equals 2x. So in this case, the answer for part B is 2x. And for part A, it's 4. I'll have to probably explain this again in class. It's a little tricky, but that's what we have for those. For number 4, you have to find the inverse for each function. Now remember, you switch x and y. So that's easy enough, right? X equals 6 to the y. But now, what we have to do is isolate y. Again, logs can help us out. Remember the basic concept I said for this, or the underlying concept, x equals b to the y. So if I have 6 to the y, then log 6x equals y. So log base 6x equals y. Again, that's the whole point of logarithms, to help undo exponents. Here, now we have a logarithmic function, so it's log base e. Remember, ln's log base e. Switch x and y. Now we want to get y by itself. So remember, we got to switch, now shift to exponential form, so e to the x equals y plus 3. So y equals e to the x minus 3. So notice how we're going from logarithm for an exponential form, and instead of adding 3 is also subtracting 3. So you can see how things are switched. Okay, last thing is graphing. Now remember, logarithmic functions, exponential functions, they're inverses of each other. So y equals 2 to the x is inverse of that function there. And y equals 2 to the x, we know if you plug in 0 you get 1, plug in 1 you get 2, plug in 2 you get 4. So if I change colors, so we expect everything to switch for the logarithmic function. The x and y values will simply switch. Plus, if you think about it, log base 2 of 1, 2 to what power gets me 1? 0. Log base 2 of 2, 2 to what power gets me 2? 1. Log base 2 of 4, 2 what power gives me 4? 2. So I have 1 comma 0, 2 comma 1, 4 comma 2. And the graph will look like this. Now in this case we have a vertical asymptote with an equation of x equals 0. Domain will now be x is greater than 0, and range will be all real. So everything's reversed. Because remember, y equals 2 to the x, we did this earlier this week, kind of looks like this, right? Where domain was all real, and the range was y is greater than 0. So notice how and we had a horizontal asymptote. So notice everything switched for logarithmic functions. So hopefully this helps you kind of get a better understanding of how this is an inverse of exponential functions. And also, think about it, we can't do log base 2 of negative 1. Because then you're saying 2 to some power equals negative 1. That's impossible. How can we make that happen? So that's why we're going to have a vertical asymptote now. Or there's going to be restrictions on the x values. Last thing is this right here. You still have h and k. So for the second graph, h is going to equal negative 3, and k is going to equal 1. So it means that we expect all the points to shift 3 to the left and 1 up. So it means that we're going to have a vertical asymptote at x equals negative 3, So our domain's going to be greater than -3, range is still all real. And the points, if I took 1, 0 and shifted it 3 left and 1 up, it'll now be over here. If I took 2, 1 and shifted 3 left and 1 up, I will get -1, 2. And if we plug them in, if we plug in -2 and work it out, you should get 1. If you plug in -1 and work it out, you have -1 plus 2 is 2, log base 2 is 1, 1 plus 1 is 2. So we know it makes sense. Okay, so hopefully you didn't find this video to be too long. Tried my best to keep it kind of reasonable. And we'll talk about some more detail on Friday. Okay, see you later. Bye.